不是这个，把它们幻灯放起来。
Well, first of all, I say that I am greatly honored to be in China and for the first time in Tianjin. And for that, thank you, Professor Fung. You have invited us. This is our 12th visit to China, and the basic occasion is that BRAIN 2013 in Shanghai. This was an international meeting. And then we have Ministry of Commerce, Government of China, and Mayor of PC meeting on, this is called GOS 2013. Government Outsourcing Meeting 2013, where myself and my wife are considered as VIP guests from Social Democrat Party from Sweden. So therefore we decided to stay in Beijing, extended visit, and Professor Fung we met in Romania, and then we decided to come here. I will briefly tell you about our research, and I can tell you that there are so many commonalities between my research and Professor Fung's team. So hopefully we will also try to establish a good relationship between our two laboratories. This was the picture taken in 2009, several years ago. So our main aim is to strengthen the relationship. The second aim is that you know that Swedish Research Council has a special program for Sweden and Chinese researchers to apply for basic research funding, and the amount could be 5 to 10 million Swedish crown, that is equivalent to same in RMB, for 5 years. So if we can do something together, I think this is a very good opportunity that we can develop our research further, and you can go and visit the site. This is www.vr.se. VR means in Swedish Vetenskapsrådet, means Natural Science Foundation. So www.vr.se, Sweden. You should go and look. Since we are working with several governments, US government, Swedish government, and many government organizations, I have to show this slide to you telling that all the views are mine, and it does not necessarily reflect the US military, US Air Force Research Laboratory, and other government organizations. What we consider is that blood-brain barrier is the key. Do we have a pointer? I can go without that. Okay, I use mouse. So we consider here that this barrier within the brain is the gateway to different kinds of neurological diseases, and any leakage to the microvessel, as you can see here, if I do this then it moves. So you can see here that any leakage of the microvessel will produce neuronal injuries and can lead to brain diseases. I am basically a neuropathologist, and he is Professor Yngve Olsen from Uppsala University. He is a renowned neuropathologist in the world. I took training under him. And then other part, we stayed with his Professor Sarvas Navarro. He is also another renowned German neuropathologist who was awarded Bundestag, prestigious German government award in his lifetime. So we have the opportunity to work these two great neuropathologists. What we feel that any kind of insult to the brain or spinal cord will alter the blood-CNS barrier. It means brain and spinal cord together, making edema, here you know very well, necrosis, ischemia, and also influences so many gene expression. All put together lead to cell death. So this is our hypothesis, and we try to intervene at different stages so that we can have good drug development. This was the book we published in 2009, and this is telling about, first book was Nano-Neuroscience and Nano-Neuropharmacology. This is a collection of 25 key reviews by experts, including us. We also have a journal called The editorial board is from various parts of the top leaders. As you can see, from NASA, US government, and European Union, many top leaders are there. My wife is acquisition editor, so you consider submitting papers here. The new area is also have support from various governments, including now Chinese government. We have some interaction. This is the leader of Indian National Party, Sonia Gandhi. She also thinks that this is the right way to go. But apart from politicians, this is Nobel Prize winner Dr. Shelley, who got Physiology and Medicine Nobel Prize in 1977. He is also our board member, and he also considered that this is the way the nanomedicine should go for the treatment of patients. This is Professor Dr. Arun Chikanover. He is Chemistry Nobel. He got 2004 Nobel Prize in Chemistry on ubiquitin expression. It's another pathological marker. We have intense discussion with him, and he also thinks that nanomedicine is the future. We have written and published this review as an invited article. As you can see, this was published in 2012, where we first time showed that, in cases of brain injury that is occurring in normal circumstances could be entirely different. For example, if you have a brain injury in an environment that is very much polluted, if you have brain injury, if you are having previously either hypertension or diabetes, then probably your brain injury will be much more adverse. And under those circumstances, you require modulation of the same kind of drug treatment. So this is the work we are carrying out with different organizations. Regarding nanomedicine, the most important point is that we should not forget the toxicity caused by nanoparticles, whether they are soft nanoparticles or they are engineered nanoparticles. So this is very important. But the point is that we cannot ignore nowadays the influence of nanoparticles either for toxicity or for drug development. Few days ago we were in Tianjin, and my friend Dr. Another Fung, Lin Yan Fung, he is there, and this is the Bethune International Peace Hospital. We are doing collaboration for a long time. So my point is that we should expand our eyes to see things in a neutral way so that we can come to right conclusion and good medical delivery to our patients. I have pleasure to inform you that some of the work that we are doing with Professor Fung in Tianjin on neuropathic pain treatment using cerebrolizing. This is a multimodal drug and a complex mixture of different kinds of neurotrophic factors. Got top 20% innovation award from US government in their recent Global Innovation Summit and Showcase meeting in Washington, DC. So we are encouraged to work, but more and more we work, I guess our knowledge is still become quite restricted. We still do not know many things, although we feel that we have discovered very many. So that is also my point. I am talking in some other aspect to you today because our global environment is not very peaceful anywhere. Lots of violence, lots of conflicts going on, and that results in war and also various kinds of missile explosion and many other things. So it is quite common that if the soldier get injured under these circumstances, probably in a desert environment, he might have intoxicated with silica nanoparticles, he might have intoxicated with other carbon and many other nanoparticles. So it is very difficult to treat under normal circumstances. And considering this organization, as you know, that spinal injuries are very common in any military. I am citing data from US military because I have some access to these data. And normally these are from United States military data. You can see that the maximum number of casualty or spinal cord injury occurs in war-related environment. And they are not occurring in normal places. They are occurring in diverse places with different kinds of gunpowder explosion, different kinds of environment, not a very clean environment. So as you can see that 53% of all gunshot wounds result in spinal cord injuries, and they are also included with various other kinds of injuries. So it's very complicated situation. It's not normal situations, therefore the treatment must be modulated. Here this is an example. The soldiers are wounded here and they have very little to treat about before they go to the specialized hospital care. So what we need, the first thing we need, treatment is very good, but if anyway we can delay or thwart the progression of pathology still for certain time, when the person is injured here, transported to the big hospital, it could take 30 minutes, 1 hour. So if we should reduce the pathology, I think we have achieved a lot. These are other examples of different kinds of environment where combat operations are going on. This is desert environment. People are breathing all the time sand or silica particles. This is a file picture from US government, and this is in desert area. Sandstorm. Sandstorms are coming quite often, and all our soldiers are breathing them almost regularly. When they are injured, either they are engaged in peacekeeping mission or they are in combat operations, their injury will be very tough than what we see on the road of Beijing by motor vehicle accident or in the United States. So therefore, these are very important. They could have a spinal injury, they could have brain injury all together, and situation is very, very complicated. Consider this scene. There is explosion, violence, carbon, sulfur, so many nanoparticles are in the air, and people are involved, get traumatic brain injury. Even some of you might be knowing that even roadside bomb explosion can produce concussive brain injury even if the person is not directly injured. Am I right? Yeah. So we have to consider these things. These are the new development, and our thinking should be modified that there are different situations. Nanoparticle exposure to the human cases and injury is entirely different thing. Therefore, we have introduced this book last year where we have discussed new perspective of central nervous system injury and neuroprotection. This is also a combination of key 20 chapters by leading authors. This is Dr. Shelley I was talking about. So we are also working on a part of this work and related to the growth hormone and brain injury. He works in Miami Veteran Hospital. So now coming, we must find new kinds of situations, and this is carbon nanotube. They are used for drug delivery. This is very primitive. It could be single, it could be multiple, and these nanotubes are filled with drugs and delivered. They can act better because the drugs are less degraded in certain time, and maybe they are slowly released for a long time. So these two factors play a very important role. This is Dr. Wang and this is Dr. Ryan Tian, our close friends. They work in University of Arkansas Fayetteville in the United States. They are the pioneer in making nanowires. Dr. Wang has synthesized together with Dr. Ryan Tian. They have a United States patent on titanium nanowires. And and we developed loading the drugs to the nanowires and delivering for spinal cord injury experimental situations. Although the nanowire was first created by Dr. Podong, he is an engineer working in Berkeley, but he has produced for electronic purposes. But Dr. Ryan Tian used it in another way and provided biological applications. Since in this department and nowadays people are working on stem cells could be very important to have become different kind of cells wherever they are transplanted. The new concept is that people are also using nanowiring of the stem cells and delivering them. This is an example that nanowires, when they were raised on nanowires, these stem cells, they live longer and the cell death is much less. This is an example that mouse embryonic stem cells, silica nanowires, they can still be lively for longer time. This is another example, cells of nanowires, they can grow very fast. These are two examples. And here you can see that they are still live and multiplying. Healthy cells, this is the example. The other use of nanowires are also that they can be used to kill especially particular cells. Here, these are in cell culture, these tumorous cells are killed by titanium based nanofilaments. The normal cells would be not affected. So this was the meeting I was talking about, this Tech Connect World, and I invite you also, if you have any innovation, you should submit. Next year the meeting is June 15 to 19, 2004, and you can find from the internet anyway. And it's a huge, over 2,500 innovations were submitted this year, and we are happy that our work together with Dr. Feng and Xinjia Yuan got 20% top innovation award. These are the communications. Since these nanowires work are very expensive, terribly expensive, so we have help from this governor of Arkansas, Dr. Mike Beebe. He would like to see that his state is doing better than other American states, and in Arkansas they are using this nanowire treatment for the arthritic patients. They put in knee operations and the recovery is much faster. This is Dr. William Slicker. He is the director of the USFDA in Arkansas, Jefferson. We are also doing collaboration on nanoparticles with his group. And some of our work was given as certificate of excellence from USFDA. Now coming to key points in spinal cord injury, there are two things very important. One is cell pathology, the other thing is functional behavior. And normally we have this rotor, you might be knowing, and this is inclined plane angle test we are doing, and I can tell you that not always these behavioral dysfunction and pathological outcome are going together. Some example of a spinal cord injury, this is very old cases. You can see that in medical history, we have some great people who were injured and could not be treated. This is another example, US President. And my point is that since then, we have not really progressed much. Of course, lots of research is going and lots of new findings have appeared, but still we do not have any cure. These are some other examples from old drawings. I will not go to these slides because some of you are very well aware what is going on, the basic point, how we can reduce the damage. And here, you are well aware in this audience, so I skip that. There are different kinds of neurotrophic factors, neurotrophins and anti-novo compounds are used to enhance neuroregeneration during cell transplantation to recover spinal cord injury. These are some of the standard methods That's how people try to replace these lost nerve cells. Some of the drugs together. And now we coming nano drug delivery here. This is important. There are two kinds of nano drug delivery at the moment. Some people use soft nanoparticles. This is lipid material. They can be dissolved and the drug can be injected into them, and they will be injected either systemically or locally. Then the shell is dissolved and drug is released slowly. The advantage of this is that the drug is lasting for longer time, and in some cases in carbon nanotube they also inject drug in the hollow core and then implant. So this also releases slowly drugs. And not only that, since carbon is a conductive material, so in cases of brain or spinal cord injury, the conduction properties are also established. These are some of the papers. So when we try to study drugs, you can see that not a single factor is involved for treatment. We need multiple factors. So therefore, there is a drug called cerebrolizin, and I think it is not very new in China. So it is multimodal. You can have neuronal survival, neuroprotection, neuroplasticity, and neurogenesis all in together. So this is a very important drug. We have tested this drug in different models, and these are the publications in brain and spinal cord injury. It works in acute cases. The drug is in liquid form, so it should be injected in milliliter, 2.5 or 5 milliliter per kilogram body weight intravenously. So we have used titanium nanowires of 20 to 30 nanometer in diameter produced by Dr. Wang. And some of the examples of these titanium wire as they look like in transmission electron micrograph, and here is in the cell culture when they are killing the cells. There could be various kinds of system. The first part is chemistry, the second part is the biology, and here is the blood-brain barrier. So if we have different modulation or different modification of the compound or the drug and tag with nanowires, they are easily permeable to this membrane without damaging it. So I will show you some of the examples in our laboratory investigation. And we have a model of a spinal cord injury where we have an incision of the right dorsal horn, T10 and 11 segment. Why we have chosen this? The point is that the model is that either you can put on weight the whole spinal cord or you make transaction. But these are not serving the clinical cases. Anyway, no model is very similar to clinical situations because there are different conditions. Always in an animal model we have anesthesia, then we put injury, but in human cases we get injured in conscious condition. The second thing is that always spinal cord injury is done from the dorsal side, but in human cases, motor vehicle accident, it always comes from ventral side. So therefore, we cannot replicate. But the point is why we have chosen is that we wanted to study drugs, and you know that we can study, this is the injured side, this is non-injured side. So we wanted to study the spread of injury this side and how drugs can also modulate or recover from the contrary side. So therefore, this model is quite unique in that way. The other point that this is unique, that we are not interested in damaging white matters, because you can see then we lost all conduction properties. So our model is limited to only gray matter injury because that can release various neurochemicals and spread it throughout the spinal cord in both caudal and dorsal direction. And therefore a drug should reduce these cell changes, not only the injured side but also the other side. So in real life it looks like this, and we are analyzing tissue samples here below and above the lesion. So this is below and above the lesion in different segments, not in the injured cell. So this is an example. If you make injury, it looks like this, untreated. If you give some treatment over this, then these two pictures are very different. These are other kinds of drugs given. So you can see that by 4 pictures, this could be the best after injury. So we can really evaluate using this model whether the treatment is working or not. So then we have loaded titanium nanowires with 3 drugs. There are some questions. Whether just nanowiring alone can make any drug working? This was the question. Or can we still see different kinds of neuroprotection by different kinds of drugs? Means if one drug is protecting 20%, other is 80%, after nanowiring, the 20% cannot be 60% or 80%. So these are the questions that we have studied. So there are 3 different kinds of drugs we have loaded on titanium nanowire. Now you see here, and the second point is that even you have nanowire drugs, it is not panacea. So we have to see at what time it should be given, at what dose it should be given. So these are one example. This is edema, and this is the untreated, first one. Here, the drug was given 5 minutes after, nanowire drug, and 1 hour after. And this is the control level. You can see that nanowire drug reduced the edema formation. This is T9, this is T12. But if it is given later, the difference still exists. So you should have a time window. The same thing happening with the leakage of iodine across the spinal cord injury. 5 minutes after nanowire, 1 drug. 1 hour after nanowire, the same drug. There are differences. These are the normal conditions. So the nanowire drugs can prevent depending on the time when they are administered. This is the leakage of advanced flu again, and this is 1 drug, 5 and 1. So we have learned this later. The second question is that we have labeled 3 drugs of different capability. If we nanowired all of them, can all have the better effects? No. This is the Tarlov scale given. This is control. This is laminectomy. The best drug that we have given is able to improve this Tarlov function only up to 2 to 4 hours. After that, after 5 hours, nothing happened. But the other drugs we are given, this is the untreated. Other drugs will have mixed effects. So the point is that nanowire drug cannot make a bad drug good drug. But what it can do, that it can enhance the property of the good drug a little further and for longer time. Due to lack of time, I am not showing. If they are not nanowired, their activity will diminish again. And here is the same thing. You can see that the best drug is always best. The second one in the middle, and the third one is not doing better. But their effect is occurring at different time points with nanowire. Using neutral analysis, you can see that we have examined blindly leakage of iodine, advanced flu, and water content. So the maximum damage occurring in this compartment, the least normals are here. And when we have given different kinds of drugs, you can see the best one are lying here, but the other one are lying here. So you can see this separation, that even nanowiring of the drugs can enhance the effect, but cannot make a bad drug working the best. This is the same thing in a better amplification. So to confirm that functional behavior can be correlated to pathological changes, here you can see that this is the nano